let's take a closer look at blackbody radiation. Now, we've already sort of implicitly used spectra in our examples so far, but I want to just be a little more explicit in explaining what a spectrum is. So you can see what we're showing here in this graph, right? This vertical axis, in this case, it's labeled as flux. In other cases, we've seen it labeled intensity. It's basically saying how much light or how bright is this vertical axis, right? On the horizontal axis, we're seeing the wavelength of light, and we see the visible range nicely illustrated here with these colors from roughly 400 nanometers up to about 700 nanometers, wavelengths of visible light. This curve is telling us how much light would be emitted at each of these wavelengths. So we could say there is some light at 200 nanometers, there's virtually no light down here at 100 nanometers, and that the peak, the brightest color of light that's being given off is maybe somewhere here about 450. Now, in fact, in this simulation, it tells us what the peak wavelength is. That doesn't mean that that's the color this object appears to be, right? We're actually seeing all the colors of the rainbow here, just in different proportions. Yeah, and so like we saw before, that's going to impact the exact perceived color that we see here, is the proportion of red, green, and blue, and all the other colors. So this spectrum is illustrating for us how much of all the different wavelengths of light we see, and this is something we're going to look in more depth later. It's a way for us, though, to see what colors of light are really coming out of an object and how that changes with the object's temperature. The first thing I want to point out is this characteristic shape of a black body. Now, to see the shape fully, I'm going to change the horizontal scale here and make it a little bit smaller so that I can see sort of both sides here. And the shape always takes this form when you have a black body radiator. Now, what we mean by a black body, it's sort of a hypothetical object, but stars behave kind of like this. What we essentially mean is that it's something which absorbs all light that comes to it and radiates all the light that comes from it. So, in other words, it doesn't reflect any light. So you and I are not very good black bodies because when light shines on us, it bounces off our skin. Right? But we still behave like a black body in that we have a temperature and we glow because of that temperature. So this is a model that we use to describe all objects if we're looking at only the light that comes from them from their own temperature, their thermal radiation. We refer to it as black body radiation. Now, regardless of the temperature, the distribution of light that comes from an object, which we see here in the spectrum, takes this shape where there's this really steep peak on the blue side and then a really long tail, gradual tail, on the red side. And understanding the shape of this is actually some complicated physics. We won't really talk about where that shape comes from a whole lot, but we want to understand the relationship between temperature and how this curve looks, right? And it changes in two important ways. The first thing I want to do here with this simulation, right, is I'm going to lock the scale, okay, because the scale adjusts itself automatically, and that can be kind of deceiving. Now, the first thing I want you to notice, though, is that when I turn the temperature down, so I have here this temperature is at 6,000 degrees Kelvin. It's very hot. It's like the surface of the sun, right? I'm going to turn it down, and notice what happens to this distribution of light. And the first thing you notice, which is really dramatic, is that it decreases substantially, right? So we went from a temperature of 6,000 Kelvin, and you saw that we were way up here at 3 times 10 to the 13, roughly. I'm going to go down to 3,000 Kelvin. I'm cutting temperature roughly in half. Okay? And where did I go down? I went way down. It's so low I can't really read it on this scale, right? But you might expect that if I cut the temperature in half, that the amount of light would be cut in half. Well, that would have only brought me to 1.5. It brought me way up here. So there's a very sensitive dependence on temperature here, right? The amount of light that's coming out depends very sensitively on temperature. We were much, much less than half, even though we cut the temperature in half. So likewise, if I go back up to 6,000, and then I go even higher, you see I go way off the scale. So I go from 6,000 to 12,000, and now I'm off this scale, and I can maybe auto-scale it. I see that I go up to 9 times 10 to the 14th. So I went up a substantial amount, right? Much more than just doubling. Right, now you've probably also noticed the other thing that's happening here, and to see this better, I'm going to leave the auto scale on, right? So we're not going to see this dramatic change in the amount of light coming, but instead we're going to look at something else. So I'm going to go back down to 6,000, and notice how this whole thing is moving to the left and right. Now again, it's still changing its vertical scale, right? Like it's getting much less, but we're looking at how it's moving to the left and right. And in fact, you can see this peak wavelength, right? Where the very top wavelength is. I can turn that on. Right, we're seeing right now it's about 859 nanometers. It's just in the infrared. And as I get brighter and brighter, hotter and hotter, the peak wavelength is getting more and more towards the blue. So now it's somewhere in the green, about 550, and now it's more in the blue. And so you can sort of see the extreme here is that when something gets really, really hot, most of this light that's here, the predominant, like the brightest part, is going to be in sort of the ultraviolet and blue end of the spectrum. And as it's cooler and cooler, the brightest part of the spectrum is going to be in the red portion of the spectrum. So we have the sense of that red actually is a cooler object, or the red light is representing sort of a cooler, right? And that as the hotter something gets, the more blue it looks. Maybe the opposite of what we use, like when you look at a faucet, right, hot and cold. But this is what the universe does. The hotter something is, the bluer it gets. Now, one of the nice things about this simulation is that we can see how this plays out with filters. We've talked a bit about astronomical filters, so I'm going to kind of change the scale here again so that we see our visible part of the spectrum, and I'm going to turn on these filters. Now you can see here, kind of like we saw previously with filters, sort of like a transmission curve. It's showing what light is coming through each of these filters. Right now it's limited by the light that's coming from this sort of fictional star, so you'll never see these filters get above that. It's just telling us how much light is in a sense being captured in each of these filters. Now as astronomers take photos of stars and they use these different filters, they can actually learn something about the color information of a star by simply looking at the brightness of the star in these different colored filters. So say at this temperature, for example, which is about 3000 degrees Kelvin, let's say an astronomer took a picture using a red filter and a green filter. What they would be able to see in this case, you can see it illustrated here with the relative strengths of these filters, is that there's much more red light than there is green light. In fact, they might even quantify that with magnitudes, something we'll talk more about later, and they could take the difference in the brightness of these things, how bright it is in red and green, and get a measurement, really, of how much more red than green this object is. And that is an indicator of its temperature. It tells us that the peak wavelength must be somewhere even further red than red, so in the infrared, right? And so it must be a cooler star. Now watch what happens as the temperature goes up, right? As I increase the temperature, and as that peak wavelength approaches green light, you can see that right about here, if I'm looking at red and green, I can see that now they have nearly the same amount of light. Again, not exactly the same, but you see this number is getting closer to zero, the difference between them. And so that tells me that the peak wavelength is shifted closer to the green. Again, that can tell me something about the temperature. And so I can go even further and eventually get to a point where there's sort of more green light than there is red light. Right? And these ratios are constantly changing. Now astronomers have precise mathematical equations that connect these magnitudes, these brightnesses in each of these filters, with the temperature of a star. So this is a way for astronomers to actually be able to measure with a pretty high degree of accuracy the temperature of any given star. Now this represents sort of an observational challenge for astronomers. How can you take a picture and from a picture get temperature, right? It goes back to some of those essential questions, those big questions we try to answer, like how hot is it when you can't stick a thermometer in the star? Well, this is actually a very robust way for us to be able to figure out the temperature of objects in space. We're not going to worry so much about these calculations. The types of calculations we're going to focus on is relating this peak wavelength to the temperature of an object, and relating the total intensity of light that's coming from an object to its temperature. Those are really important relationships that are going to allow us to learn more about stars and ultimately give us more tools to help measure the distance to various objects in space.